All right, so this video is going to start the waves unit, so let's get going on page 2. So it talks about energy transfer and waves. So there's 3 types of waves we need to talk about. So one would be conduction. Okay, so conduction is the transfer of energy by contact. So that is the key phrase there. So they have to actually be touching. So an example would be like if you touched, okay, a hot stove. Okay, so you have to physically touch it for it to be conduction. Now, convection, okay, that is the transfer of energy through a movement of liquid or gas. Okay, so via current. So that's like if you heated up water. So if you heat up a bathtub and you move that water around, you feel that heat moving through the water. Or like if you actually hold your hand above a stove or above, like say, above a pot that's hot and you feel that steam. Okay, so you're not actually touching the pot. It's actually the transfer of heat through that steam to your hand. Okay, and convection is usually directional. So that means it usually goes upwards. So like heat rises and cold stays towards the bottom. Okay, so convection is just that transfer through air or liquid, usually directional. Now radiation, okay, that is energy through electromagnetic waves. So those are things that we'll talk about here in a minute that don't require a medium at all. Okay, and they travel in all directions. Okay, so radiation goes all over the place in a straight line. Okay, so a good example of radiation would be something like getting a sunburn. Okay, so you're not actually touching the sun. The sun's far away, so it's not actually moving particles towards you. Okay, it's actually those light waves that are actually heating you up. Okay, so that would be radiation. Now, an actual wave is the transfer of energy in the form of a disturbance through a medium. Now, what it means by medium is you can have either material or nothing. Okay, but it has to go through something, so it's either going to have material or it's going to be nothing, like in space. So, waves transfer energy, but not matter. Okay, so the matter is not actually moving, it's just the energy is moving from one thing to the next. Okay, and all waves require a source of energy. Now, waves can be classified into 2 categories. You have electromagnetic waves, which do not require a medium, so I mean they can travel through space, because remember, space is a vacuum. There's nothing there. There's no particles. Okay, versus mechanical waves have to have something to transfer to. So there has to be some type of particle there to transfer. So real quick down here in the summary, I'm going to kind of do this first before I do this next section. We covered this in chemistry, so I'm sure all of you remember this. There was your EMR waves, your electromagnetic radiation. So if anybody remembers that phrase that red Martians invade Venus using X-ray guns, okay, so you had radio. Okay, so this one had the high wavelength, which we'll worry about that stuff later, okay, and low frequency. And then it went micro. So microwaves, and then infrared. And then we had visible light. So remember, those were your colors, your Roy G. Biv. Okay, and then we had UV light. Okay, so UV. And then X-ray. And then gamma. Okay, so at gamma, that was your very short wavelength, but high frequency. That's what makes it damaging. Okay, the more waves you have in a second, the higher frequency you have, which makes it more dangerous. That's why radio is not that bad, versus gamma, that would be pretty bad. So these EMR waves do not require a medium, or don't require an actual mechanical, they don't actually require a material medium, sorry. So they do not require, if I could spell, a material medium. So all these can travel through space. Okay, so when we go up here, it says which type of waves are the following. Okay, so again, mechanical does require a material medium. So water, that is a material medium. So this is going to be mechanical. Okay, then you have light. Well, light's a part of my EMR scale, so this is going to be electromagnetic. Infrared, that is also on my electromagnetic. So it really does help to have that EMR scale down, because that kind of just tells you exactly what it is. Now sound, it does require a medium, so you need air particles for that to happen. So if you were to scream in space or something like that, or there's an explosion in space, you're not going to hear it because there are no particles to transfer that sound. Now, X-rays, that's on my EMR scale, so that's electromagnetic. Radio, that's on my electromagnetic scale. Wave in a rope, so you actually have a physical rope, so that's mechanical. UV, that's on my EMR scale. Wave in a spring, you have a spring, so that's actually a material, so that's mechanical. And then gamma, that's going to be your electromagnetic. Okay, so it really does help to have those EMRs written down, so that kind of tells you what's mechanical and what's not. Okay, so a source of energy will produce a wave pulse. Okay, so a wave pulse looks like this. It's basically just a single disturbance down the line. Okay, so the way I think of this is think of the garden hose. Like, have you ever been pulling a garden hose and it gets stuck on something? Okay, so rather than you walk all the way back to unstick it, okay, if you just whip a pulse down to that hose, okay, hopefully that pulse will go far enough where it gets off whatever it's stuck on, and now you're good. So that is what basically a pulse is. Now, a continuous wave is when the pulse just keeps repeating over and over. So that looks more like a normal wave. Okay, so it just keeps happening over and over and over again. Okay, so I'm going to talk a little bit about wave, and we'll talk more about the actual specifics here in a little bit. So remember, we had wavelengths. Okay, so your wavelength is one full wave. Okay, so that is your wavelength. Okay, and we had the character lambda. That's like the upside down Y. And again, we'll talk more about this. So this is just kind of get you refreshed a little bit. So wavelength has to be one full wave. So it could be down here. Okay, it could start here and end here. So you could go all the way to there. Okay, so again, a wavelength, which is the upside down Y. So if you ever see the upside down Y, that's me talking about wavelength. It has to be one full up, which that's called a crest, which we'll talk about later, and one full down. And that is called a trough. Okay, so in order to be one full wavelength, there has to be one full up and one full down, or basically start and end at the same spot. Okay, so moving on to types of mechanical waves. Our first one, so mechanical, remember that requires a material. Okay, so our first is transverse waves. That is where the displacement of the medium is perpendicular to the direction of the wave moving. So what's happening is I'm moving the wave up and down with my hand, but the wave is actually traveling to the right. Okay, so that's called transverse, is when that movement is perpendicular to each other. Okay, so like if waves in a piano or a guitar string. So when I'm strumming a guitar string, I'm using my pick, it's going up and down. Okay, but if you ever actually take a slow motion video of a guitar string, okay, the wave of the string, or the guitar string, is actually doing this. Okay, it's going up and down as it's traveling towards the end of the guitar neck. Okay, so that is what a transverse wave looks like. Now moving on to a longitudinal wave or a compressional wave, that's like a slinky. Okay, so the displacement of the medium is parallel. Okay, now you could make a slinky go up and down, like you could just whip it like this where it makes a transverse wave. Or what you can do is you can actually take your hands and actually go, pretend like you're closing your hands and then stretch them out, close your hands, stretch them out. Okay, that is the example of a compressional wave. Okay, so a compression is when that slinky bunches up right here. Okay, and then a rarefaction is when it stretches out. Okay, so energy, so what's happening is your compressions are going left and right, and the direction of the slinky is going left and right. So that is parallel. Okay, so examples in deep water and sound waves. Okay, so sound does not look like this. Okay, that is a transverse wave. Okay, sound actually looks like this. So what you have is something that creates an energy or a pulse or sound. It actually is a compressional, so it gets bunched up, and then it starts to stretch out, and then it starts bunching back up again. Okay, that is what a sound wave actually looks like. So that's a longitudinal wave. Okay, or you have a deep ocean. Now, ocean can get a little tricky because it's actually both. But deep oceans, what happens is, what makes those waves is you actually have waves that go up and down. Okay, so just kind of drawing that there. Is your wave the energy is going up and down, okay, and the wave itself is actually going up and down as well. Okay, so if those are parallel, okay, that is longitudinal. Now, we'll talk about ocean waves here in a second because that is a mixture of both. Okay, so number 3, surface waves. Okay, so this is what I mean by it's a combination of transverse and longitudinal. Okay, so you have the top of the wave, you have the surface going up and down, and it's moving towards the right. Okay, but at the same time, you still have these compressional waves going up and down. Okay, so it's actually a mixture of both transverse and longitudinal. Okay, moving on to the next one. So we'll do a real quick summary, and then that will end this video. Okay, so we have waves. Okay, we're going to break those into 2 categories. Okay, first I have electromagnetic. Okay, so remember that was your radio, microwave, infrared, visible, UV, X-ray, and then gamma. Okay, now remember these do not require a medium, so no material medium. Okay, so they can travel through space and they're fine. Okay, these were considered transverse. Okay, now your other type is going to be your mechanical. And this one is, so this one does need a material. So material medium. So it needs something like either air particles, water, an actual object like a rope or a slinky. Okay, that's what I mean by material medium. Now we can break that down into 3 categories itself. Okay, it can be transverse. So I can take a rope and I can throw pulses down there. Okay, and my hand is going up and down, but the direction of the rope is going left to right. Okay, so that would be transverse because it's perpendicular. Or it can be longitudinal. Okay, I can take that same slinky, okay, and I can compress it back and forth so it looks like this, where it's like stretched out. And then it starts coming back together and then it starts stretching out again. Okay, so that is your longitudinal. And then you have your surface wave. Okay, so that's like in the ocean where it's just a mixture of both. Okay, so that'll end this video. So we'll start on page 6 on the next one.